Okay. So today we will start about classification in machine learning. So yesterday we discussed what is machine learning. So let's see how many of you can just explain that in short terms. Please write it in the chat. So what is the first thing that comes to your mind when we talk about classification? What should be the very first thing? A hint, maybe something related to the data. Grouping, no, grouping means we are doing some sort of unsupervised learning. Okay. Data amount. Why the data amount? You can use a huge data set for any type of work. Oh, no, I didn't ask about machine learning. I asked about classification. Classify the data based on different categories. Okay, cool. That is, we try to predict a class or some contiguous label, or rather a discrete label for some data. Okay, but what do we need to do this? What do we need to do this? Some feature of supervised learning that we need for classification. Okay, nice Orkodipto. We need some labeled data. Okay, so what does it mean? Suppose I have a flower data set. Okay, so I might have sepal width, petal length, etc. But this will vary for different types of flowers, right? For rose, the features will be different. For hibiscus, the features will be different. And so for each of the features, I will be assigned a label, say for some features x1, x1, x2, x3, x4, I have the labels assigned as hibiscus. Then say y1, y2, y3, y4, I have it assigned as rose. Okay. So I will have a label indicating that these features help you identify this class. Okay. Cool. Is it clear, everyone? Thus think it with respect to a school. Suppose we are considering 10 classes. Then for each class, they will study different subjects. These subjects can be considered as the features of students. So if you are studying physics, chemistry, maths, biology, there is a higher probability of studying class 9 or 10 compared to class 6, right? So clear? Okay. So let's see what is this fuss all about. Okay. So classification is a supervised learning task. What do we do in this task? We try to predict the class level. Okay. And which is discrete. That means it will not be of some value. Rather, it will indicate the class number or the class name. So, for example, if I want to predict if my email is a spam email or is it not a spam email, or if I have gone through a credit card fraud, or is my credit card transaction quite authentic. Okay, So we have already talked about classification versus regression in yesterday's class. So in classification, we predict categories, whereas in regression, we predict about some values. For example, in regression, we can predict the house prices, whereas in classification, we can predict if a mail is spam or if it is not a spam mail. Okay, you have various applications of classification like spam detection. You can use in medical diagnosis. For example, if you see an X-ray image and if you want to say that if there is a tumor, you want to detect the tumor and you want to claim if it is cancerous or non-cancerous. You can have sentiment analysis, you can study movie reviews, and you can say if the movie is about happy, or you can predict the genre of the movies, so on. There's detection, image recognition, where you see, for example, you can do a face recognition task where you can learn from the features of of a face image, of a facial image, and you can classify it to which person does it belong. Okay, then there are two primary types of classification problems, that is binary classification, where you have two classes. Okay, so it will be either a 0 or a 1, or yes or no, spam not spam, or cat versus dog classification. And in case of multi-class classification, you have more than two classes. For example, if you are trying to recognize handwritten digits, then you will have 10 classes, 0 to 9. These are some of the popular classification algorithms, like k-nearest neighbors, support vector machine, decision trees, random forest. So these are quite trivial these days. You can have plenty of material online, so you can study these on your own. But today we will primarily focus on neural networks. Okay, for classification. So do you guys have any doubts till now? Or is there anything you would like to ask? Okay. So let's proceed. So what is neural network? What is a neural network? So what comes to your mind? Don't Google or anything. Just think of the term neural, and what occurs in your mind. Okay. So when we come across the term neural, so the first thing or the first word that comes to our mind is a neuron. And why do we need a neuron? Basically, via a neural network, we try to emulate the human brain, and we try to mimic the nature of a human brain. How the patterns are created in our human brain, we try to recognize that. And how does that occur in the nervous system? It occurs through neurons and synapses and transmission of electric signals, right? So if you touch a hot cup of tea or a hot cup of coffee, so if it is way too hot, as a reflex action, you will remove your hand from the cup, right? So why is that so? Because the sensory neurons, they receive the data, they receive the signal that it is hot, and it transfers it to your brain. Okay, which makes you do that action. And similarly, so next time if you see a cup of coffee or a cup of tea, you will first want to look into it, that if it is hot or not, and then you will grab it, right? So your brain, it has already recognized the pattern that if I am served a hot cup of tea or a hot cup of coffee, if I grab it immediately, there's a high chance that it might seem too hot and I might burn myself. Not burn myself, whatever. Okay. So is it clear? Okay. So now we come across the first neural network, the very first neural network, which is a perceptron. So in case of a perceptron, we have several input neurons and then we process it into another neuron and gain some output. So perceptron is essentially a binary classifier. That means it can classify into two classes, true or false, 0 or 1, or class 1, class 2. Clear? So just try to think of it. If I work with respect to logistic regression, what are the pointers that might come into my mind? What are the things I need to train here? In case of perceptron as well, you'll try to fit a linear separable line that can separate the data into two classes, just like a logistic regression one. So just think of it. Which part? Which part do you want me to repeat, Ashraf? Perceptron. Okay. So perceptron is essentially the first or the basic, most basic neural network. Okay. And to do this, we need certain nodes or neurons that are accumulated together and then we obtain a response in some other node. Okay. Here, weird sign after summation in. That is also called a step function. This one, right? This is also called a step function. So it's just like sigmoid. You can also call it signum function. Basically, you'll have a 0 or 1. That is all about it. Hmm. Okay, so what was the question that I had asked? So what if you yeah. So what if you think of it in terms of logistic regression? Is it similar to it if I do a binary classification? I am doing a binary classification. So first we need the input data, right? So for example, you have a data set m cross n. The first sample, it represents the first row represents the first sample. You pick up all the features and each feature gets fitted into each of these nodes. Okay. So x1, x01 will be fitted here, x02 will be fitted here, and so on. Here. Okay. So then for each of these a vector will be fitted, right? Yeah, a vector will be fitted. Okay. Now, for each of these neurons, I have an associated weight to it. Okay. So, and then I perform an added sum of weights. Okay. So, as you can see, that summation I is equal to 0 to n wi xi. Okay. And for x0 equals to 1. So, can you guess what is x0 equals to 1? We have done this in yesterday's class. X0 equals to 1. Why do this? Theta 0, exact. That is, basically we are doing W0. W0 becomes my theta 0, x0 equals to 1 means the equation turns into W0 plus W1 x1 plus W2 x2 and so on. Okay. And then if that summation is greater than 0, I have 1 else minus 1 as my output into two classes. Okay. You can also fit a function over here. To do that, that will be called the threshold function or step function. So it will be f of the added sum of weights. Clear? So now just think of it in terms of logistic regression. What were you doing? You were trying to optimize y equals to, or rather y hat equals to theta 0 plus theta 1 x1 plus theta 2 x2 till theta xn. And just we are similarly doing that in case of the perceptor. Okay, w0 plus w1 x1 plus w2 x2 till wn xn equals to what? Y, right? Y cap. So both these equations look similar, correct? Okay. So here are the official terms that we need to see. Right. Okay. So n being my number of input variables, y is equal to fz, that is my output. You have the set of training samples x1 comma d1, where x1 is your input feature vector, and d1 is the label associated to it. That means it is my uh, technically it is y, and the y here is y prep, but yeah, you can consider it to be the original level, and y being my predicted level. Here xj, each x is basically a row vector as mentioned here, xj0, xj1, and so on. And then you have dj, that is the desired output value of the perceptron for the input x, that is by label, class label. You have xji, that means the jth that means the ith feature of the jth training sample. So and you have xj0 equals to 1. So xj0 is basically my offset or intercept. In terms of neural networks, we call it bias. Yeah, we call it bias, bias. Okay, it just means that it is just the offset, just like the intercept in case of a straight line, right? Here, now this is the algorithm step. So first we will initialize the weights randomly and the threshold for it, that what value should lead to 1 and what value should lead to -1 or 0 in this case, whatever you want. Then for each sample, you calculate the y. Oh, could I please explain the bias part? Okay, so bias is basically an offset, which means say y equals to w0 plus w1 x1 plus w2 x2 till wn xn. Okay, so this w0 acts as my bias, which is the default value of y when all the other x values are 0, which is my intercept if we think it in terms of a straight line, right? Here, oh, okay. So for each sample, I calculate the y predictions, the predicted values via this weighted sum, and then I pass it through a function. So somehow the slide got deleted. Then there are few more steps. I'll just create it now. Don't you worry. Okay. So somebody has drawn this annotation line. The person could delete this. We could. Okay. So whatever. Yeah. So I have it now. Step 2. Then we need to update the weights. Okay. So here it is given a plus sign. You can also do a minus. Okay, so both ways are correct. So this is basically gradient descent, and if we had a minus, that would be gradient descent. Okay. So it's preferable that you use the minus operation here. Okay. So now, can you guess how to get this formula? Any idea from the previous day's class? How can we achieve this? Any guesses? Performing iterations. Yeah, you will be performing iterations. But based on what do you get this update formula? Y is equal to mx plus c form. Yeah, all right. But I want to know, how do I receive this update formula? Even in yesterday's class, we got an update formula, right? Using gradient descent, aggregate of MSE. So what do you mean by aggregate of MSE? By calculating loss function, then we do something on the loss function to receive this formula. What? Okay, so Kushumita has said the correct answer, which is using gradient descent, which means that we need to minimize the cost function or the loss function, right? So if you just partially derive this formula with respect to what quick answers. So last day we were optimizing M. So we were derivating with respect to M. So what are we optimizing in this class in case of perceptron? Think. You must be able to say this. WM, which is my weights. I am trying to optimize with respect to my weights. Okay. So I will partially derive this equation with respect to S. So in yesterday's class, somebody had asked me, sir, what if instead of square, I do the modular sign? See, it has been done here. Sorry. Okay. And if you partially derive this formula with respect to W, you will get this update equation. So T being the current weight values for T plus 1th iteration or epoch, I can update my weights using this formula. Okay, clear? Anybody, any doubts till now? So it is the root mean square cost function. Yes. Okay. So do you have any doubts till now? Shall we proceed? Repeat the steps again, sir. Okay. So first we randomly initialize the weights. Okay. Then for each sample, I try to predict its output. Okay. So after I am done predicting, I look at the difference between the original prediction and the original class level and the predicted class level, right? So, and we try to minimize that error. So we repeat this step to again and again, which is basically calculate the wipe rate, then modify the weights, and so on, until we reach our loss convergence criteria. What is a loss convergence criteria? When the change between two loss values is very minimal or insignificant. Okay, repeat step 3. So step 3 is basically the loss function. Okay, so once I have calculated the loss value, if it is a bit too high, so I check between two loss values, the difference between two loss values. So until and unless there's very insignificant change between two loss values, say loss t and loss for t plus 1, if this difference is very insignificant, only then can I say that my model has reached an optimum stage, an optimum training stage. So then I can say that my training is complete. Okay, so this was for training and perceptron. Clear? Any doubt? Okay. Okay, so does anybody else have any doubts regarding this? So now this section of the perceptron training, IRMEK-A2 means whatever. Okay, so now this section of calculating the loss function and updating the weights is called the learning of a neural network. What is DJ? DJ is my predicted output, the original class level. See, it is the original class level. And Y here is my predicted class level. Clear? Okay. So this segment of calculating the loss value and then optimizing the weights is called the learning of an algorithm. So any neural network has two essential parts, one being the architecture and second being the loss function. Okay, so what is architecture? So my number of nodes and number of layers. So in case of multi-layer perceptron, we'll also see that there are several hidden layers. Okay, so number of nodes, number of uh, hidden layers, the activation function used, the loss function is called the architecture of the neural network. And what is learning of the neural network? So when we are optimizing the weights with respect to the loss function, the loss value calculated, this is my learning. Okay, clear? So far so good till perceptron. So shall I start with multi-layer perceptron? Okay. So in case of perceptron, this could only classify between classes that are linearly separable. So what about non-linear data? How do we deal with that? How do we deal with this? Anybody? Any ideas? So here comes the concept of using non-linear activation function. Now what is an activation function? Okay. So what is an activation function? So basically we say if you recognize some patterns, I will activate a few neurons. That is, I will fire these neurons. Okay. For example, this node here. So if you are classifying between uh, an apple and an orange, so an apple is of red color and an orange is of orange color, right? So suppose this first neuron here will be activated in case of a red color, and this orange will be activated in case of the orange color. These nodes here will be activated in case of an orange color. So what is this? This is basically that these neurons will send some value when it recognizes certain patterns. Okay, so this is done through the help of activation functions, which are non-linear in nature and hence helps us deal with the non-linearity of data. So do you understand activation functions? Mm. Okay. So what are activation functions? Okay. So suppose I have recognized some pattern. For example, I have an apple and I have an orange. An apple is of red color and an orange is of orange color. Okay. So suppose the first neuron in this hidden layer gets activated when I encounter this orange color, and these two nodes get activated when I encounter the red color. So both of these neurons will provide us some values when these specific colors are encountered. Okay. So suppose this will give a value of 0.9 when it comes to red color. This will give 0.85 when it comes to red color. But in case of an orange color, it will give 0.25, 0.1, and so on. Okay, cool. So when we identify certain patterns, we activate certain neurons. Hence the term activation functions. Okay. So do you understand it? That is, we fire up some neurons so that they can pass on the value to the next neuron, next layer of neurons rather. Clear? Okay. So each of these neurons, the values of each of these neurons shall be calculated using a function and the weighted sum of the inputs received in this layer. Okay. So this value, say this is hij, hij value of h, so sorry, this is hi. So hi will be function of the weighted sum over all these neurons. As you can see, x0 is connected to this neuron, x1 is connected, x2, then xn minus 1 and xn. So basically f of, you receive a connection here from this neuron, say w1, and this is h1. So you have h1 w2 w1 plus and so on. So hij will be function of w1 to x0 and w1 x2 w1 xn till, sorry, w1 xn. Clear? This will be a weighted sum. Okay. So now, for each of these neurons, you will receive some values after passing through these activation functions, and then they are forwarded to the next layer of next hidden layer of neurons, and finally to the output layer in the same manner. So this part is called the forward propagation. Clear? So did we understand forward propagation? Do we have any doubts till forward propagation? So when we ultimately receive the value of y, say this output neuron trades the value of y, this is called my forward propagation. Clear? Okay, so does anybody have any doubt regarding forward propagation? No, not only through activation function, you calculate the values of all these neurons. Okay, then you calculate. So suppose there are two hidden layers, H1 and H2. Okay, so you receive the input data. You then calculate that the weighted sum for each neuron, and each neuron is passed through a function, and then you receive some value. This value is again passed to the next hidden layer. Okay, and similarly, you calculate the weighted sum for each neuron, then these neurons are passed through some function, which is the activation function. Okay, till we finally get to the output node where we calculate the output, say y is equal to something. Okay, so these from receiving the value to calculating the output y is equal to whatever, that is my activation function. That is my forward propagation. Sorry, this entire process is my forward propagation. Clear? So now here again, we will have something known as the cost function to calculate the amount of error through several activation function. It undergoes forward propagation. Yes, you can say so. Several activation functions receive that is the output of several hidden layers. And then you ultimately get to the output node. This entire process is my forward propagation. Clear? Okay. So here again, we will have a cost function to minimize. That is yi minus yi cap. This yi being the original levels, yi cap being the what predicted levels. Okay. So we are calculating the mean square error again, and then we need to optimize it. Now I need to optimize these layer first and these two. So what are the optimizing parameters here? The weights. So first, so backpropagation is a very beautiful example of what chain rule in differentiation can do. So first, I will optimize the loss function. I will partially derive the loss function with respect to the weight here. Say this being V and this being W. So the weight function, the weight matrix between input layer and hidden layer is W, and the weight matrix between the hidden layer and the output layer is V. So to optimize this V, I will need to partially derive this equation, the cost function, with respect to V. And then to optimize weight matrix W, I need to optimize Y, that optimize the cost function with respect to W, and then use gradient descent again. So here it will be V new equals to V old minus eta into del cost by del V, and here it will be W old, W new equals to W old minus eta or learning rate into del cost by del W. Clear? So we optimize these values, this, and then we go through a forward propagation again, and then receive the output node values. And this one process of forward propagation and then a back propagation involves one entire iteration or one whole epoch. Okay, and then we undergo several epochs until we reach an optimal state, which is called the loss convergence point. Okay, and when we can say that the model has converged. Clear? So did you understand this part? Both forward propagation, back propagation. See, back propagation is a bit tricky, so feel free to ask questions. Okay. Yes, I will repeat it. Oh, I'll repeat the back propagation part. Okay. So till forward propagation, we had calculated the cost function, right? That is MAC equals to, till forward propagation, we had calculated y cap. Okay. Now I need to check if this y cap value is accurate or not. That this might be erroneous. So I calculate the cost function. Okay. I guess you all understand this cost function. 1 by n summation over I is equal to 1 to n y minus y I cap whole square. So you all understand the cost function. Okay. Now I need to optimize my model so that the error is minimum. So just like in perceptron, we were optimizing a set of weights, right? So there I had only one set of weights, but here I can have multiple set of weights. For example, let's just focus between the hidden layer and output layer. So these connections, these are my weight values. So I'll have a weight matrix. Let's name it V. Okay. So just think in the case of perceptron, I had my weight value as W, and then I was optimizing the cost function with respect to W. So here I need to optimize my V because this is my trainable parameters, right? So I will optimize this V via partially derivative of the cost function with respect to the weight matrix here, that is V. Correct? Till this, are you clear? Are you clear till this part? Anybody has any doubt? Till this V, the hidden layer and the output layer. Partial derivative of the cost function with respect to V. Here? Okay. So once we are done with this part, then using gradient descent, we will update the weight values. We will update the weight values. That is V new equals to V old minus eta, which is my landing rate. Consider it as yesterday's alpha. Okay. So is the weight update value here? Okay. So just consider it to be V. V is equal to veta into this eta. Eta is called my landing rate. And this is my partial derivative. So this will basically be V new equals to V old minus eta into del cost by del V. Correct? Clear? Then we have found the new updated V. Okay, so we are done with this part. Now what? Now we need to update this weight matrix, which is W. Then I'll partially derive the cost function with respect to W because see, I want only to optimize W here. V has already been optimized. I just want to optimize W here. Okay. So I will partially derive the cost function with respect to W and then again use gradient descent. Then I will get new weight values via W new equals to W old minus eta into del cost by del W. Clear? Clear? The optimization of weight matrix between input and hidden layer. Is it clear? Okay. So once we have updated the weight matrix between the input layer and the first hidden layer, so this entire process is backpropagation. Now, again, in the next epoch, I will calculate the value of the hidden layers and then I'll calculate the values of the output with this updated weight matrices W and V. And thus, I have completed one epoch which consists of one forward pass, that is the forward propagation, and one backward pass, which is the back propagation. Clear? Clear? Do you have any doubts? I don't mind repeating this again. When does an epoch end? After updating W's or V's. Both. First, you need to update V and then update W. So the back propagation is the optimizing and updation of weights. Correct. Correct, Mahi. Okay. So why is it back propagation? So forward propagation, it is a feed forward style. Like you have you have traveled in this forward direction from input to the output, then you need to optimize it, so you need to travel backwards, right, in the backwards direction. So basically you're taking a u-turn, right? So you update the v first, because this falls first in your back propagation path, and then w. Clear? So it will be a set of forward and backward propagation for optimization, or rather you can say for one epoch. So one epoch means a set of forward propagation and a backward propagation. Okay, so one epoch has two parts: one forward propagation, then two backward propagation. Clear? Correct. Forward is for y plate to obtain the value of y plate, and backward is for updating the weights. Correct. Here, can you look into the algorithm? Do I have a green signal? Okay, cool. So we have looked into this. Then okay. So here m is my number of layers. Then n being the neurons in one layer. So if this is layer j, then nj means 3, right? Then xp is basically the number of samples. Xp is the number of features in one sample. Basically one row vector. Okay. So TP is the corresponding to training output rate to the training samples. Okay. OP is the actual output. So this is the output that we have calculated, and this is the original output. Okay. Then we have the Y values, that is the output from the final layer. Cool. And this is the weight connection. And then we have the error associated to it. Okay. So first we initialize the weight connections, then we train that to the corresponding output. Okay, then pass the values to the input layer using this yji equals to function of this, where f is my activation function. So here they have used the sigmoid function here. Okay, and then obtain the output values for each row, for each column rather, for each hidden layer, and then we train the final matrix with respect to the weights in the backward order. I get this del ji yji, and then I repeat this step 2 till step 6 to ultimately train the model. Here, so if you have just understood the whole working system of this multi-layer perceptron, you can later sit quietly and just focus on the notations, and you will see that it is very simple. It is very simple. Okay. So, do you have any doubts regarding this? Regarding classification? Any questions that you feel like you want to ask? No, it is called eta. So in physics, we have studied efficiency, no? Mechanical advantage by something. So you used to denote it by eta. So this is that notation, eta. Here, anybody else any doubt? Otherwise, we can look into the code part. So for the code today, we will learn something new called PyTorch. We'll try to design the MLP through PyTorch. I guess things will be pretty much self-explanatory. You won't face much doubts. Okay. So can somebody please provide me the naming convention again for the Google Drive that I used to follow? I forget it every time. So uh, so first we need to import a few things that I'll just copy paste. Oh, before this, let's just look into. So this is how I load iris. Okay, I have used something here from data sets. I am importing this via which I can load the iris dataset. Okay, so from this I will separate the data and target as iris.data. Then we need to scale the data. We use something known as fit transfer, which is basically the original data minus mean by standard deviation effect. Okay. Okay. For this fit transfer, hello, for fit transfer, the scale feature, yeah. So basically, we are just scaling the data as the say let's say it's x. So x minus mu, the mean of the data by standard deviation. Clear? Then we need to do a train test split of the data. Yes. Then we use this random state. Okay. So 42 is a seed value that will follow for splitting the data randomly. Okay. And by mentioning test size equals to 0.2, I say that make it a 80-20 split such that 80% of the data is used for training and 20 is used for testing. Okay. Then we need to convert it into some data structures known as tensors. Okay. Because these algorithms like PyTorch and all, TensorFlow, they work with respect to tensors. Tensor is basically an array of matrices. So we need the input data, then we have the output data. Okay. So can you explain what I did with this output team? You should be able to say you have studied this in class, in the Python basics class. Mm, let's see. Length of set y. So why I'm using set y? Why am I using the set function? To get output of what? Output of what? Output of samples. No, no. Think properly. What is my y? What is my y? What is y? Let's break it down. What is y? It is my it is by target labels. That is the class labels, right? So there might be. So I can consider, just think of it as a list that contains the class labels. Okay, I have several uh, values in it. Okay, so if I have three classes, one, two, three, there will be multiple occurrences of this one, two, and one, two, and three, right? There will be multiple occurrences of one, two, three. So how do I know what are the number of classes in the data set? Okay, so when I use the set function, then I will only have the unique occurrences of each y value. So if it has multiple occurrences of 1, 2, 3, I'll have just 1, 2, 3. So then I'll calculate the length of it to get the number of unique nodes in the output layer. Okay. So in the output layer for a multi-class classification, okay, let's look into this image. So for a multi-class classification, I will have three nodes here. Okay. 1, 2, 3 in the output layer. So class 0 will be denoted by 1, class 1 will be denoted by one node, and class 2 will be denoted by another node. Clear? Is it understood? So this is why I need to calculate the output dimensions. Okay. So let's keep two hidden layers as of now. So let's have hidden one. So done till now. Now we need to create the multi-layer perceptron. Okay. So let's just declare a class called myMLP, which is the object of the class. The class name is myMLP. Okay. So we'll look into this layer values train and all later. But first, let's look into the MLP class. What is a node? Node is a neuron. A node is a neuron. Good. So let's declare class multi. Yeah. So this will be a good recap for your OOPS concepts as well. So what is this? What am I doing this? Why did I use NN dot module? What does this mean? Mhm. Anybody? Why are we using NN dot module within brackets? Hello. Anybody? Come on, you have studied this. You should be able to say this. Hello. So have you heard of the concept named inheritance? Hmm. So basically, we are inheriting an inbuilt class and n dot module, which is basically a PyTorch module so that we can build our neural network. Okay, understood. See how simple this was. So now def init. What is this def init? Quick answers, please. So one, I have two questions. What is def init and what is the meaning of self? Initializing the model. Basically, it is a constructor. So you have heard of the term constructor. Yes, correct, Sridham. It is a constructor. Okay, and what is self? Where are you using self? Self is the object itself. Correct. Good. No, self is basically the object itself, and it also means So NN module is an inbuilt PyTorch module that we can use to build neural networks. Okay, so I am inheriting this NN module class and then I'm using it for my own needs. Okay, okay, so just let me write this part and then I'll explain it properly. Till then, you guys try to map this. What can this actually be? Okay, can you guess what I am doing with this input comma hidden one? Focus on this and then look at this image. Making hidden list, yes, obviously, but what does this essentially connect? So it basically connects the input layer to the first hidden layer, right? Maps input to the hidden layer, correct? Okay, so it basically connects the input layer to the hidden layer. Okay, and then basically hi equals to what it is doing is consider the hidden layer matrix to be h. Then h equals to of some function of x into w, right? Correct now. And what is this function? This function is the activation function. Aha. So this function is the activation function. Here we call it ReLU. So what is ReLU? ReLU means rectified linear unit. So what does this do? Basically, say if I write value of x, then it will be a value between max of 0 comma x. So if you have a negative value, it gets turned to 0. If you have a positive value, then it stays as it is. Okay. Softmax is another activation function mostly used in the output layer to give the probability. Okay. So I'll just pause the meeting for a bit. Okay. And I'll give you 5 minutes. Okay. Just try to focus on this. Visualize this with respect to the model. Okay. The architecture, what the calculations are, or what I'm trying to build. Okay. So I'll be back within 5 minutes. Till then, just try to visualize it. Okay. Positive value remains same. Yeah. Hello guys, I'm back. So is the screen not visible? Okay, so who would like to explain? It is visible. Okay, thank you. So who would like to explain this, what I have done till now in the multi-layer perceptron class? The screen isn't visible. Now? Now is it visible? Okay. Why did this happen? Okay. Okay, so let's just put in a couple of more minutes into focusing what this happens, what happens in the class multi-layer perceptron till now. So we are still in the constructor part. Okay. And we are just declaring the architecture. Okay. We are layering down the architecture. So just think with respect to this image. So mm, just think with respect to this image. Okay. So rather, uh, let me just show the entire screen, this structure. Is there no option of slide? Haha. How do I show you this image? For now, let's do it like this. Can do the cut off. Can anybody suggest me some technique so that I can show both these together? Okay, I guess the visibility is a bit better now. Is it? Drag the side part towards the left. I did drag it, but there's nothing working with this. Is there no option to hide? Okay, done. Okay, so now focus on this image. Now think of it. So what have we done here? So basically, when I say input comma hidden one in a linear structure in nn dot linear, I am basically developing a weighted connection between the nodes of the input layer and the nodes of the hidden layer. Okay, so basically in line 14, why h1 and h2 are connected? Because I have two hidden layers. So after hidden layer 1, I will have another hidden layer. So they need to be connected as well to reach the final layer. Okay, understood? Understood, Shresh? There is a connection between the hidden layers. Yes, exactly. So is it clear? Okay. Then basically, how was the equation framed? No, y is equal to function of summation of w x0, w0 plus w1 x1 and so on. Right. Okay. So this linear function is equivalent to that. Then we stack an activation function on top of it to get the hidden layer values, thus completing hij equals to function of the weighted sum, right? So clear? I guess it's clear till now. Mhm. Cool. Just give me 1 second. While I can close this. Yeah. So far so good. Now we need to do the forward pass, obviously. So def forward. So we have used this function sequential to wrap this entire network into one object. Okay. So the forward function is pretty simple. So I have the input data here as x, and then I say that I will return self dot mlp network x. Okay, so that's my forward part. Okay, now next I need to build the model self explain my plan it's best comma. Okay, so the optimization or the gradient descent is done through this. So this is a technique, an optimizing technique similar to the gradient descent. Weight decay is a parameter that says the depreciation value of the weights. Okay. So I'll set a loss function here. For this case, we'll use cross entropy loss. It is somewhat similar to emission, I guess. Loss function is cross entropy. Yes. What is convergence criteria? I'll explain that. Convergence criteria means when should the model converge. Okay. So here by convergence criteria, I mean that if the difference between two loss values, that is for the loss value for epoch t and for epoch t plus 1 is lesser than 1e minus 3, that means the loss change is insignificant and hence the model should converge or the model should stop. So here I call upon the optimizer to do the gradient descent step and then I back propagate using loss dot backward. Okay, and optimizer step to update the values. Okay, then I check first is okay. Yeah. Then I would like to have a function that will calculate the layer values for me. Okay, the values of each in each layer. Model converges at epoch means uh, model converges at this iteration. Okay, epoch That means after training the model for these many number of times or iterations. Excuse me. Yes, correct. Yeah. Before that, so later you can look into this function in, at peace because you might find it tricky, but this is just to calculate the values in each of the hidden layers and the output layer. Okay. Let's compile this and see if it has worked properly. Multi-layer perceptron not defined. Mm. D means dimension. Okay, so this was a bit too much. Model converged after two epochs. So I expected a bit more epochs. So in the algorithm that I had trained, I got around 267 epochs. The classes হয়নি বাকি maybe if I set the convergence criteria to 1 minus 5. So it takes a lot more epoch to convert, or rather, let's keep it someone in mid. We are done with training and test with training numbers, right? Okay. So now we need to evaluate. Okay. So how will we do this? So my red train, it is essentially from the last layer. So I will just calculate using dot argmax. You know argmax and argmin, right? For the position. So that will essentially mean that this neuron has been selected as the prediction for this. Okay. That's it. That's just so I need this function called okay, so far so doubt so far so good. Do you have any doubts till now? Hmm? Tata. Okay, so do you have any doubts till now? Till the model evaluation? Okay, so we are detaching this because we will use scikit-learn library which does not work on tensors. So we are detaching it from tensors and then converting into NumPy arrays. So it's already quite late. Let me just copy this part. Copying this part immediately. So I have different metrics like uh, different evaluation metrics like uh, accuracy score, precision score, recall score, F1 score. Then there is something called the Cohen-Kappa score, something known as Matthews correlation coefficient, Jaccard score, to measure if my model has performed nicely. Okay, so let's see. Migrate test. Okay, so I'm getting a bit too good result for this very ideal case. But again, this is for a very basic data, and these days models are quite strong, so they can perform this. So at 1e minus 3, the model does not converge properly, and so obviously, as you can see, the results are pretty bad. And at 1e minus 4, let's see if I change the convergence criteria. It's okay, 3.5. Oh, I can't do it as 3.5. No. Let me split as 0 to half. Correct. So at 1e minus 4, I get a very good over exaggerating results. But we can claim that our model has not been overfitted because the training results are lower than the testing results. So it does that the MLP models these days are way too good and advanced. Okay, it has changed a bit now. So it depends on the training data set as well. I think this would be more ideal compared to what I had done. Okay, so did you understand this code? Anybody who would like me to explain any portion? So did you understand classification, MLP, perceptron, and whatever we have studied? So I guess now you will be conversant in understanding the deep learning classes as you have. Can you tell us from start till end what you did? Okay, definitely. So first, I have loaded the dataset. Then I have scaled it. I have divided the dataset into trained dataset and test dataset. Okay. Here, trained dataset and test dataset. Then I need to design the model. Okay. For that, I need a few things known as the input dimension, the output dimension. Why? Because I need to automate the input layer, okay, and the output layer depending on the dataset. So if I change the dataset, I wouldn't like to manually update this, right? I would like my program to get the value automatically. Just fix it. কাগজ আটকে গেছে নাকি দেখো তো প্রিন্টারটাকে পেছন থেকে খোলো ওখানে প্রসুন্দর একবার করেছিল কাগজ আটকে গেছিল ওখান থেকে খুলে বার করেছিল কাগজ থেকে Okay, so sorry for the interruption. Okay, so then I have done the input part. Then I have created two datasets. Obviously, we have uh, kind of hard coded it, but later, if we want, we can also automate it. Then we would need a loop here. and then it would have been done. Okay. So then I have created a class multi-layer perceptron, and there I have defined the model architecture. I have defined the functions for forward layer, and this model function controls the entire training part of the training part, and in the end we also calculate the test values. That mostly, but consider it for mostly the training part. This the operation of the new MLP model is controlled through this function. Okay, what have we done here? First we have declared the optimizer, then the loss list, and then the convergence criteria. Then we have also declared the loss function, and then we start with the training. Okay, so one epoch is one loop iteration. So first we go through the forward pass, then we calculate the loss value, and then we find the current loss value, then we store it in a loss, so later, so that later if we want we can print a loss curve. Then we calculate the gradients, we start the back propagation and update the values. Done. Then I calculate the difference between the loss functions, the loss variables. Okay, the loss values. Sorry. So if the difference is way too insignificant, then we say that the model has converged, so you can stop at this point. Okay, so no more training. Then we have calculated the trained layer values for each layer, and we have also calculated the test layer values for each layer, with our intention being that we need to pick up the values from the output layer so that later we can do the predictions. So once this is done, this section is complete. Then I calculate the training values and the test prediction values. So argmax basically produces the index of the last element. Okay, so I take the last column, the last layer value. Okay, so it is in the form of a tensor. Then I select that which position from the x-axis. Okay, or rather, yeah, from one means y-axis. From one axis has the maximum value. So that will be my class level for that sample. Okay, clear? So we are doing this, and then we have the evaluation matrix function so that I can evaluate how good the model has performed. Clear, Ashaf? Okay. So does anybody else have any doubt? So both section 1 and section 2 have uh, deep learning classes in the next curriculum. Section 2 has. Okay. Cool. Okay. So are there any more doubts, or I think let's call it a day? No doubts? Okay. Let's pause the sharing. Okay, stop share. Pause the recording. Stop recording.